In this video, we are going to study how to find Laplace transform of piecewise continuous functions. But before that, let us understand what is meant by piecewise continuous functions. In my last video on Laplace transform part 1, we have seen that Laplace transform of ft is a definite integral from 0 to infinity e raised to minus st into ft dt, which is a function of s, capital Fs, where s is positive. Please note that here ft is continuous in whole of its positive domain from 0 to infinity. Sometimes this domain is split into different sections, and for each section ft is defined separately, and it is continuous within the boundary of that section. For example, ft is 0 for t between 0 and 1, it is t for t between 1 and 4, and it is 0 again for t greater than 4 up to infinity. Here, for each section of the domain 0 to 1, 1 to 4, and 4 to infinity, ft is defined separately. For first section it is 0, for the second it is t, and for third it is 0. We find that ft is not continuous in whole of its domain from 0 to infinity, but it is continuous within the sections 0 to 1, 1 to 4, and 4 to infinity. And this is known as piecewise continuous function, and we are going to see how to find Laplace transform of such piecewise continuous functions. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. You can even check playlist of this channel. Perhaps you might find videos that you are looking for. In finding Laplace transform, we often have to deal with integration of product of two functions. When we integrate product of two functions, say fx into gx dx, then the rule is first function into integration of second minus integral derivative of first f dash x into integral of second gx dx and integral of whole of this with respect to x. Instead of using this rule of integration by parts, it is often convenient to use method of continuous integration by parts. In this, we use continuous differentiation of fx, and we denote it by f dash x, f double dash x, f triple dash x, etc., and continuous integration of the second function gx, and we denote them as gx1, gx2, gx3, etc. So we write continuous integration by parts of product of two functions fx and gx dx as first function fx into first integration of the second gx1 minus first derivative of fx f dash x into second integral of gx2 plus second derivative of fx f double dash x into third integral of gx3 minus third derivative of fx f triple dash x into fourth integral of gx4 plus so and so forth. So here we have to start with fx, then f dash x, then f double dash x, then f triple dash x, and in case of integrals, first integral gx1, then gx2, then gx3, then gx4, so and so forth. And importantly, we have to use alternate signs, plus, then minus, then plus, then minus, then plus, so and so forth. This is very convenient and you can find integration by parts in one go. Find Laplace transform of ft equals t for 0 less than t less than 4, ft equals 5 for t greater than 4. Laplace transform of ft will be integral from 0 to 4 e raised to minus st into t dt plus integral from 4 to infinity e raised to minus st into 5 dt. Integrating by parts, this will be t into e raised to minus st upon minus s minus 1 into e raised to minus st upon minus s into minus s s square from 0 to 4 plus 5 into e raised to minus st upon minus s from 4 to infinity, which is 4 into e raised to minus 4s upon minus s minus e raised to minus 4s upon s square minus 0 minus e raised to 0 upon s square plus 5 into e raised to minus infinity upon minus s minus e raised to minus 4s upon minus s. This is minus 4 upon s e raised to minus 4s minus 1 upon s square e raised to minus 4s plus 1 upon s square plus 5 upon s into e raised to minus 4s. So Laplace transform of ft will be first this 1 upon s square plus 5 upon s e raised to minus 4s minus 4 upon s e raised to minus 4s will be 1 upon s e raised to minus 4s minus this 1 upon s square e raised to minus 4s, which finally will be 1 upon s square plus 1 upon s minus 1 upon s square into e raised to minus 4s. ft equals 2 for t between 0 and 3. It is t for t greater than 3. We have to find Laplace transform of ft. Laplace transform of ft is integral from 0 to infinity e raised to minus st into ft dt, which is for the first interval integral from 0 to 3 e raised to minus st into 2 dt plus for the second interval integral from 3 to infinity e raised to minus st into t dt. It is 2 into e raised to minus st upon minus s from 0 to 3 plus by integration by parts first function into integral of second e raised to minus st upon minus s minus derivative of t 1 into integral of the second function e raised to minus st upon minus s into minus s from 3 minus 2 upon s e raised to minus 3t minus e raised to 0 will be 1 plus when we put t equals infinity, both these terms will vanish and this will be 0 minus now we will put t equals 3, so minus 3 upon s e raised to minus 3s minus 1 upon s square e raised to minus 3s, which is minus 2 upon s e raised to minus 3t plus 2 upon s plus 3 upon s e raised to minus 3s plus 1 upon s square e raised to minus 3s. So Laplace transform of ft will be first this 2 upon s, then this 3 upon s minus 2 upon s will be 1 upon s, so plus 1 upon s into e raised to minus 3s plus this term 1 upon s square e raised to minus 3s. This is 2 upon s plus 1 upon s plus 1 upon s square into e raised to minus 3s. That will be 2 upon s plus 1 upon s square into e raised to minus 3s. So this is Laplace transform of ft. ft equals 0 when t is between 0 and 1. It equals t when t is between 1 and 4, and it is 0 when t is greater than 4. In a piecewise continuous function, in each of its subintervals 0 to 1, 1 to 4 and 4 to infinity, ft is continuous and limit ft as t tends to the endpoints of these intervals are finite. First, we will draw the graph of this piecewise function. We have ft is 0 when t is between 0 and 1. It is t between 1 and 4 and 0 from 4 to infinity. So the function is continuous between 0 and 1 here, between 1 and 4 here, and from 4 to infinity here. Now we will find Laplace transform of ft. So LFT is from 0 to infinity of e raised to minus st into ft dt, which is integral from 0 to 1 e raised to minus st into 0 dt plus integral from 1 to 4 of e raised to minus st into t dt plus integral 4 to infinity of e raised to minus st into 0 dt. Integrating by parts, it is 0 plus t into e raised to minus st upon minus s minus 1 into e raised to minus st upon minus s into minus s from 0 to 4 plus 0. So LFT will be minus 4 upon s e raised to minus s into 4 minus 1 upon s square into e raised to minus s into 4 minus 1 upon s into e raised to minus s minus e raised to minus s into 1 upon s square. This is minus 4 upon s e raised to minus 4s minus 1 upon s square e raised to minus 4s plus e raised to minus s upon s plus e raised to minus s upon s square. So Laplace transform of ft will be this e raised to minus s into 1 upon s plus 1 upon s square minus this e raised to minus 4s into 4 upon s minus 1 upon s square. So this is how Laplace transform of piecewise continuous functions are found out. If Laplace transform of ft is capital Fs, we have to prove that Laplace transform of f of at is 1 upon a capital F s upon a. A thing to remember here is when t is multiplied by a in its Laplace transform, it goes in the denominator. Laplace transform of f at is definite integral from 0 to infinity e raised to minus st into f at dt. We have to evaluate this integration by method of substitution. So we will substitute this at equals u so that t will be 1 upon a u and its derivative dt equals 1 upon a du. In this substitution, when t is 0, u is 0, and when t is infinity, u is also infinity. So we write the Laplace transform of f at as integral from 0 to infinity e raised to, from this substitution, minus s into u upon a into fu, and for this dt from here 1 upon a du. This we rewrite as this 1 upon a integral from 0 to infinity. We write this as e raised to minus s upon a u fu du, which is 1 upon a, and for this integral from this and this we write capital F this s upon a, which is Laplace transform of f at. Hence proved. Viewers, if you like this video, please click the like button. Share this video with your friends and classmates. Subscribe to this channel. Post your constructive comments to make the videos better. You can even check playlist of this channel. Perhaps you might find videos that you are looking for. See you in the next video. Until then, keep watching Number Collage. Thank you.